Hi, I'm Professor Melko, Chemistry PhD, and today we're going to talk about stoichiometry, percent yield, and limiting reactant. And a lot of students in chemistry think limiting reactant problems are
just plain evil.
but we'll make it simple for you. Let's jump into the lecture. We're going to start this lecture with a stoichiometry practice problem. Now, I have a whole previous lecture that lays out the 4 parts of solving a stoichiometry practice problem, so feel free to go back and watch that video. But I want to sort of start this lecture with a stoichiometry practice problem, since limiting reactant is really just 2 stoichiometry problems in one. Okay, so let's spend some time solving this. Feel free to pause the video here if you want to try to solve this one on your own before I go ahead and solve it. When solid zinc reacts with gaseous oxygen, so the first thing we need to do is write the reaction. Right, that's the first step, is write and balance the chemical reaction. So here we have solid zinc plus gaseous oxygen. Oxygen is one of these special diatomic molecules, right? So it looks like this. It yields solid zinc oxide. And zinc is one of these elements, it's a transition metal, but it's always basically 2+. Oxygen is always 2-, so it's a 1-to-1 ratio there. There's the chemical formula for zinc oxide. Now I need a 2 here and a 2 here to balance this reaction. So that's step 1 of solving any stoichiometry problem. Now I'm going to go through and convert the given grams to moles. Okay, that's part 2. And we recognize this as a stoichiometry problem, not just because it says stoichiometry at the top, right? But because it's asking for a mass and it's giving a mass. So this is a mass to mass stoichiometry problem. So starting with the given grams, 2.40 grams of zinc, I have to convert this using the molar mass of zinc. That is always the first step. And our molar mass of zinc given down here is 65.39 grams per mole. Grams goes on the bottom so that it cancels with the given unit. Okay, so that's step 2 here. After we balance the reaction, convert this thing to moles. You can punch this into your calculator and complete this calculation, or you can keep going onto step 3, which is now convert this moles of zinc. Give myself a little bit more space here. Convert this moles of zinc to moles of the thing we want, zinc oxide. So I need to use my second unit factor here as a molar ratio between zinc and zinc oxide. Zinc goes on the bottom because it has to cancel. And to get the numbers in front of these units for the molar ratio, I look to the balanced chemical reaction. That's why we had to do this, because we're going to need this molar ratio. And this ratio says there's 2 zinc oxides, so a 2 in front of zinc oxide here, for every 2 zincs, so a 2 goes here. Now I have the unit left, moles of zinc oxide, and the last step of the stoichiometry problem is to convert this moles of zinc oxide, put the unit down here in the bottom, 2 grams of zinc oxide, I'll put the unit in the top, since ultimately that's the unit I want, grams of zinc oxide. So this is grams per mole, that is a molar mass. I get that by adding up this 65.39 from zinc with the 16 for oxygen to get the molar mass of zinc oxide. So that should come out to be, what, 81.39, oh, wrong place, that is grams, 81.39 grams per 1 mole. And now that unit goes away. And now I have everything I need to calculate this. So I do 2.4 times 1 times 2 times 81.39, just multiplying across the top. Divided by 65.39, enter, divided by 2, enter. I should get out at the end 2.99 grams of zinc oxide. Okay, so that's my final answer here. So that's one mass-mass stoichiometry problem. In limiting reactant, we're going to have to do 2 of these problems for the price of 1, basically. And we'll show you how to do that. But let's first introduce the concept of limiting reactant. In a limiting reactant problem, the concept here is that there's a certain reactant. So here we had 2 reactants, zinc and oxygen. One of these is going to limit how much of that zinc oxide I can make. Okay, it's going to be used up before the other reactants. So in previous lectures, we sometimes talked about conservation of mass, and you can use that if you have exactly the right grams of each reactant, such that they cancel exactly, right? But it's more practical that a lot of times in chemistry, you have an excess of one of these reactants, right? Zinc might be expensive, and so you might only buy 100 grams of it, but oxygen is a lot cheaper, so you might have thousands of grams or kilograms of it, right? And so that oxygen might be in excess, or you might just be getting the oxygen from the air in the room, right? So that's in excess, and the zinc is going to limit the reaction there. But what we're going to try to do here is solve quantitatively which of these reactants is limiting the reaction. And to do that, we have to do these stoichiometry problems. Okay? The other reactant, of course, would be in excess. So if in this reaction zinc was limiting the reaction, oxygen would be in excess. There's another analogy here I like to use, which is building a grilled cheese sandwich. Everybody likes grilled cheese, right? You need 1 slice of cheese and 2 slices of bread, assuming you're poor like me and can only afford 1 slice of cheese for your grilled cheese. Sad. Sometimes this is the reality, though, right? So 1 slice of cheese and 2 slices of bread make 1 sandwich. So I go to my drawer in my fridge. I have 5 slices of good old American Kraft single cheese and 8 slices of bread. I have enough cheese for 5 sandwiches, but I only have enough bread for 4. So the bread is limiting how many grilled cheeses I can make, right? And the cheese is in excess. So shown visually here, right? Here's all the bread I have. Here's all the cheese I have. I actually have a 5th slice of cheese. I can't make grilled cheese. So what happens to the 5th slice? It's in excess. I give it to Mr. Wiggles here. He's earned it. Love this little buddy. Yum, yum, yum. He likes the cheese. Anyways, in chemistry, right, this is going to look something more like this. We might have 5 nitrogen molecules. 1, 2, 3, 4, 5. Okay, and we might have 9 hydrogen molecules. I'm just going to write this faster to write this out. Now, if these things are reacting together to make ammonia NH3, there's a certain ratio that has to happen, right? Usually when we balance a chemical reaction for N2 plus H2 makes NH3, the balanced chemical reaction would look like this. 2 nitrogens for every 3 hydrogens to make 2 ammonias. Nope. That's not right. 1 nitrogen with 3 hydrogens makes 2 ammonia molecules. Now that's balanced. Okay, but maybe I have 5 nitrogen molecules and 9 hydrogen molecules. Okay, well, each of these nitrogens is going to combine with 3 of these hydrogens. This nitrogen combines with 3 of these hydrogens. This third nitrogen combines with 3 of these hydrogens. And now I've used up all the hydrogens, right? So the nitrogen, these 2 are in excess. They're left over at the end of the reaction. We usually don't write this, though. Okay, and we only say the ratio of what is actually reacting, right? But here in chemistry, I might have extra nitrogen around when I run this reaction. So the nitrogen here would be in excess, right? Here's the balanced chemical reaction we would usually write. The hydrogen here would be the limiting reactant. Okay, a lot of times, though, we're not talking about the molecules. We're talking about the grams or the moles of these things that are getting reacted. Okay, so here's the really method we're going to use to solve these limiting reactant problems. Okay, first we need to calculate which reactant is limiting, and we'll run out first by following these steps. Okay, first we're going to do a stoichiometry problem for one of the reactants going to the product. So just like all stoichiometry, that's mass-mass. We convert the mass of the reactant to moles of the reactant to moles of the product with the molar ratio to mass of the product. We're going to do the same thing with the other reactant, convert it to moles of product, and then mass of product. And then we're going to compare these 2 masses at the end. So we've done 2 separate stoichiometry problems, and we compare the results. The limiting reactant is the reactant that produces the least amount of product. Okay, so that's essentially saying maybe reactant 1 runs out first, and maybe this number right here is lower. Okay, that means reactant 1 here is limiting the reaction, and reactant 2 makes a lot more. It's capable of making a lot more product, but reactant 1 runs out first. Okay, so that's what we're trying to do here. Let's see this in action. So here's a problem where we're combining iron oxide and aluminum. Single replacement type of reaction. Here's the balanced chemical reaction. What we would have to do if we have 25 grams of each reactant, we would take the 25 grams of iron, use the molar mass of iron to get moles of iron. Iron oxide is what's given here. That's the reactant. The moles of iron oxide. Then I go to moles of the thing I want. How much iron is made? So I take that moles and use the mole ratio to get to moles of iron. Then I'm going to take that moles of iron and use its molar mass to go to the grams of iron. And I'm going to do the same thing down here, except for the other reactant, grams of aluminum. And do the same thing to get to grams of iron. And then I'm going to compare these two numbers, pick the smaller one, that's the actual amount of grams I will make, and the reactant that corresponds to that will be the limiting reactant. But you have to actually go through and calculate these numbers, so that's what I'm showing here. 25 grams of iron using its molar mass, using its molar ratio with iron, and using iron's molar mass. That makes 19.4 grams of iron. You do the same thing starting with the aluminum and its molar mass, its ratio with iron in the balanced chemical reaction, and again the molar mass of iron. It can make 78 grams of iron almost. So clearly FeO here is limiting the reaction. Why? Because it's only capable of making 19. There's enough aluminum to make 78 grams, right? But we're only going to make 19 because the iron oxide runs out. And we need this iron oxide in order to make the iron. Okay, so if we use up all the iron oxide, we make 19.4 grams of iron. Okay, so iron oxide here is the limiting reactant. Since it's making the smaller number, aluminum would be in excess. Let's try another one now, and pause the video here to try to write out this reaction and solve the stoichiometry problems and compare the end results before you watch me solve it. First part of this is to write this chemical reaction. If you're still struggling, and I find a lot of students, even at this stage, might be okay with the math and the conversions, but if you don't get the formula right when you write it out, you're not going to be able to do the math correctly. You're going to get the wrong answer at the end. So a lot of students still struggle with writing the chemical reaction and getting all the formulas right. So let's go over that here. What mass of cobalt-3 sulfide is produced from cobalt metal and sulfur? Okay, so the balanced chemical reaction, cobalt is reacting with sulfur. Neither of these are special diatomic type of elements, so they're just by themselves. And we're making cobalt-3 sulfide. The 3 in Roman numerals means when it's combining, cobalt has a 3+ charge. Sulfide means sulfur, and it usually has a 2- charge, which means I cross these numbers over to get the formula cobalt-2 sulfur-3. Okay, so I have to balance this over here with a 2 in front of cobalt and a 3 in front of sulfur. So that's my now balanced chemical reaction, the first part of any stoichiometry or limiting reactant problem. And now with that in mind, I can take the 0.75 grams of cobalt metal and convert it to, what am I asked for? Mass of cobalt sulfide. I know I'm going to have 3 steps here. Mass of cobalt sulfide at the end I'm after. And I know the 3 steps are going to be a molar mass, a molar ratio, and then a molar mass. Okay, first is the molar mass of cobalt. It is 58.93, looking on our periodic table down there at the bottom, grams per mole. Now I need to go from moles of cobalt to moles of the thing I'm asked for, which is cobalt sulfide. And the chemical reaction is where I get these coefficients becoming the moles in this mole ratio. 2 cobalts for every 1 cobalt sulfide. And lastly, I need the molar mass now of cobalt sulfide. So I get that again from the periodic table, 58.93 times 2 plus 32.07 times 3. I get a molar mass here of 214.07 grams per mole. And now I multiply everything across the top, divided by the bottom. I get 1.36 grams of cobalt-2 sulfide. Cobalt-3 sulfide, excuse me. Okay, so that is answer 1, but that's just the first half of this problem. I need to do a whole nother stoichiometry problem, now considering the sulfur, the other reactant. So let's do this on another slide. 2 cobalt plus 3 sulfur makes cobalt-2 S3. And so now I have to start with the 0.35 grams of sulfur. Same kind of setup here. Only here now I need the molar mass of sulfur, which is 32.07 grams of sulfur per mole of sulfur. And now I need the mole ratio of sulfur to cobalt-3 sulfide. From the balanced chemical reaction, it's 3 to 1. Lastly, I need this molar mass of cobalt-3 sulfide. And in these stoichiometry problems, or in these limiting reactant problems, this last molar mass is the same because I'm comparing the same product. So it's still this 214.07 grams per mole. Calculating the answer. Looks like I get 0.779 grams of cobalt sulfide, assuming I did all the math right. Now I've done the 2 stoichiometry problems necessary in this limiting reaction problem, and I compare the answers, 1.36 versus 0.779. I choose the lesser of these numbers. So what mass of cobalt-3 sulfide is made? The lesser of the 2 numbers, this. So I actually make 0.779 grams of cobalt-3 sulfide. Sulfur would be the limiting reactant if I was asked for that. Cobalt here would be the excess reactant. And sulfur, the limiting reactant. Because sulfur makes the least amount, it's going to run out first. The question is really asking how many grams do I make? Well, I make this lower number, 0.779. So that would be the final answer here. Okay, so that was a limiting reactant. The last concept I want to talk about in this lecture is percent yield. And this goes sort of hand in hand with limiting reactant. A lot of times you can use limiting reactant to exactly calculate how many grams should I make. Okay, if I actually have 0.75 grams of cobalt, I weigh that out in the laboratory, and I combine it with 0.35 grams of sulfur in the laboratory, I should make 0.779. But we're not all perfect. We might spill a little bit, right? We might accidentally add something we're not supposed to. And so at the end, the product we get may not weigh exactly 0.779 grams. And so we often speak about percent yield. The theoretical yield here is what we just calculated. So when you're thinking about theoretical yield, this is usually what you're calculating, right? You're doing the math to figure out how much should I make in this limiting reaction approach. The actual yield, you'll see words like what you measured or experiment. Okay, that's different than just sitting down with pen and paper and working out what you should be able to make. Actual is what you actually make in the laboratory, what you measure at the end from your experiment. Okay, the percent yield compares these two values. It takes this actual yield that you get in the laboratory and divide by theoretical yield and times 100 since it's a percent yield. So let's look at what a question might look like for percent yield. Assume you calculate at the end a 33.3% yield. What is the actual yield if the theoretical yield is 9.5? Okay, well, I know percent yield is actual over theoretical times 100. So as long as I remember this is the formula, I put in 9.50 grams for theoretical. And I'm asked for what the actual yield is. So I'll just call this question mark or X or whatever placeholder you want to use. And now it's just algebra. Divide both sides by 100 to get rid of this. And now I have 0.333 equals X over 9.50 grams. And so now I multiply both sides by 9.50 grams. It drops out on the right. It appears on the left. And so X here is equal to 9.5. times 0.333, and I should get a number here for X, which is the actual yield, 3.16 grams. Okay, rounding to 3 sig figs as was given in the problem. Okay, so that's one type of problem you could get for percent yield. Okay, so in today's lecture, we did a stoichiometry problem. We then talked about limiting reactant and how that's really just 2 stoichiometry problems for the price of 1. Right? And then covered percent yield here at the end. That'll do it for this lecture. As always, if you like this video, please push the like button and feel free to subscribe to this channel on YouTube or catch me over on Twitch every week where I do office hour streams and answer whatever chemistry questions you might have. That'll do it for this lecture. I'll see you next time.